Verifying the bug. In the previous lesson, we crafted a proof-of-concept exploit, a skeleton designed to overflow a vulnerable buffer within VLC Media Player 0.86d. That file, constructed in the .ssa subtitle format, was intentionally malformed to trigger a crash when VLC attempts to parse it. Now that we've built our skeleton exploit, it's time to verify its impact. Today, we'll analyze the crash, examine the state of memory, and confirm whether our input reaches the execution path of the program, especially whether it affects EIP, the instruction pointer. This is where exploitation becomes investigative. We're no longer just feeding input, we're tracing its journey through memory. In this step, we will transfer the malicious .ssa subtitle file to the target Windows XP machine. In preparation for the exploit demonstration, we will rely on a lightweight HTTP server, which offers a simpler and more seamless method for file delivery within the lab environment. Begin by serving the file from your attacker machine using Python's built-in HTTP server. This command spins up an HTTP server listening on all interfaces at port 8000, making the .ssa file accessible via a web browser. Next, access the Windows XP virtual machine using Remote Desktop. Adjust the IP address if needed to match your environment. Once logged in, open your web browser and navigate to the IP address of your Kali machine, followed by the port number. Locate the target file in the directory listing and download it directly to the XP system. Let's begin by launching Immunity Debugger and loading the VLC.exe binary. In Immunity, go to File, Open, and select VLC.exe. Ensure the process pauses at the program's entry point. You should see the disassembly view showing the entry instructions. Also, look at the bottom right corner of Immunity. The word paused should appear highlighted in yellow. This confirms that the debugger has successfully attached and is holding execution at the correct location. Before proceeding, I'd like to improve visibility by adjusting the font size. The default font in Immunity may appear too small and difficult to read. To change it, right-click anywhere in the debugger interface and select Appearance, then Font. From the list, I'll choose Font 6, which provides much better legibility for our demonstration. If you're opening Immunity Debugger for the first time, the interface might seem overwhelming. Let's demystify it by breaking down the main panels you'll be working with. Registers window, top right. This section displays the current values held in the processor's main registers, including EIP, the instruction pointer, ESP, the stack pointer, and others. These are essential for tracking how and where your payload interacts with the program. Disassembly view, top center. This is where you see the actual instructions that the CPU was executing at the time of the crash. If your exploit worked correctly, this view may show invalid or nonsensical instructions, evidence that EIP was overwritten. Stack window, bottom left. This shows the contents of the stack at the moment of failure. It helps you determine whether your input made it into the stack frame and whether values like ESP now point to a region filled with your buffer. Memory dump window, bottom right. This panel shows a raw view of memory, byte by byte. It's especially useful for identifying recognizable patterns, such as long strings of repeated characters like A, typically represented as X41, and for visually confirming that your input propagated deep into memory. With these windows in mind, you can now methodically examine the aftermath of your exploit's execution. Press F9 to allow the program to continue running normally, or simply click on the play button. Now that VLC is active inside the debugger, Open the previously crafted .sa subtitle file from within the player. Immediately, VLC will attempt to parse the file. Due to the excessive payload, it will exceed the buffer limits and crash. Immunity will freeze the process and raise an access violation exception, exactly what we were hoping for. But let's pause here. We're not celebrating a crash for its own sake. We want to analyze it. Before attempting to control execution or redirect code flow, we need to observe, not assume, what's happening at the moment of failure. This step answers two critical questions. Did our crafted input reach the stack and cause a crash? Did it reach the point where we control key registers like EIP? This verification lays the foundation for all later stages. If we can't confirm the buffer's reach, any further step becomes guesswork, and we don't build real exploits on guesses. Once the crash occurs, turn your attention to the top right pane in Immunity, the registers window. Here, you will notice that EIP contains non-repeating characters. At this point, it is evident that while the crash was caused by our input, the EIP value does not yet confirm clear control. It might be pointing to arbitrary or corrupted bytes that aren't part of our deliberate pattern. To investigate further, we need to step through the crash path and observe how the program arrived at this state. Now hit Shift F7, Shift F8 and Shift F9 respectively to manually step through instructions. After a few iterations, you'll notice that EIP eventually gets overwritten with the value 41, 41, 41, 41, our repeated A characters. This is a critical moment. It confirms that with proper stepping, the program does reach a point where EIP is under our control. The appearance of x41 string means our input has not just reached the stack, it now dictates the path of execution. In exploitation terms, we control the instruction pointer. At this point, we want to assess the full scope of our buffer's reach. Begin by examining the structured exception handler, SEH. Go to the menu bar in Immunity Debugger. Navigate to View, SEH Chain, or press Alt+S. In the SEH view, observe whether any handlers in the chain have been overwritten. If you see entries like x41 string, it implies that the buffer extended far enough to corrupt exception handlers. This confirms another potential exploitation path via SEH overwrite, though our current focus remains on direct EIP control. Right-click the entry holding the 41 string. Then choose Follow in Stack. In the memory dump window, you'll see a repeating sequence of 41 string, representing A character, a strong visual evidence that our buffer has filled the stack and overwritten EIP. If you're seeing a full column of 41 string, you've reached the moment of full control. To fine-tune control, let's go back to the attacker machine and revise the buffer length. Open your Python exploit script. Replace the overly large buffer size, 500,000 characters, with a more manageable 200,000 characters. Save the file and regenerate the .ssa payload. Return to the Windows XP machine. Restart VLC.exe inside Immunity Debugger. Download the new VLC bof.ssa file. Then open the updated subtitle file to trigger the crash again. This time, The crash should occur cleanly and more reliably. Inspect EIP again. It should now immediately display the x41 string value on crash, confirming a successful overwrite without needing additional stepping. In the stack view, you should see an uninterrupted sequence of x41 values, the hexadecimal representation of A. Again, take a close look at the ESP register. It should be pointing to a memory region filled with a string of A characters. These visual cues confirm that our input is clean, deliberate, and fully under our control. Why this matters? In C and C++ programs like VLC, user-supplied data, such as subtitle files, is often passed into fixed-size stack buffers. Our buffer has exceeded that size and spilled into adjacent memory, including the saved return address. This is definitive proof of a stack-based buffer overflow, direct overwrite of control data, and a potential for code execution. We are no longer speculating, we are demonstrating with precision. Let's step back and summarize the technical milestones we've achieved in this lesson. We confirmed that our crafted buffer reliably reaches the vulnerable memory region, propagating deep into the stack. We triggered a consistent, reproducible crash, which is foundational for any successful exploit. We verified that EIP, the instruction pointer, is overwritten with our input, specifically with the x41 string, proving beyond doubt that we now control execution flow. We observed our payload across key memory regions, the stack, ESP, and even the SEH chain, gaining a full view of how our input affects program state. We refined our buffer size, reducing it from 500,000 to 200,000 bytes to improve stability, manageability, and execution control. At this stage, our project is no longer a blind brute force attempt. It's evolving into a tactical exploit with surgical precision. We have achieved the essential milestone, reliable EIP control. The next step is to pinpoint the exact offset where that overwrite occurs within our buffer. This will allow us to align redirection instructions and, eventually, inject shellcode with accuracy. In the next lesson, we'll use Metasploit tools to calculate that offset, transforming our controlled crash into a structured redirection mechanism. Before moving on, challenge yourself with the following practical tasks. These exercises are designed to deepen your observational skills and strengthen your control over memory manipulation. 1. Vary the buffer size incrementally and observe the outcome. What is the minimum buffer length that still triggers a reliable crash and overwrites EIP? 2. Experiment with different filler characters, such as B x42 or C x43. Track their flow through the register's stack and memory dump windows. Can you visually confirm their presence across key memory regions? 3. Investigate the SEH chain. At what point does it become corrupted? Is there a stage where structured exception handler-based exploitation becomes possible? The more you test, observe, and reason through these memory behaviors, the more intuitive exploit development becomes, eventually allowing you to read the stack like a book and manipulate execution flow with confidence.